This presentation is delivered by the Stanford Center for Professional Development.
Oh, we're on. How about that? Hey, everyone. Welcome. I don't have any handouts for you today. I actually want to finish up the implementation section of the course. I think I'll get through it today. I'll make it a point to finish it today. Come Monday, we're going to start talking about multi-threading, and I'll even preface that a little bit today, provided I don't run out of time. Remember that your midterm is Wednesday evening over in Hewlett 200, the largest room in this end of campus. 7 to 10 p.m. It's open note, open book. You can bring printouts of your programs, whatever you need. Just plan on taking the exam in a 3-hour period. It's designed to be more than enough time for the midterm. Okay. There's also the technology talk right after this class right here over in Hewlett 201. So you can go visit Hewlett 200 to see what room it's like for the exam. But in 201, there'll be a technology talk from 12 to 1 o'clock. Okay. I left you last time with this example, but I got several questions about how it worked, which probably means that I rushed through it in the last 5 minutes of class, which is probably true. We had something like this, whoops, where I declared an int array of length 4, an int I to serve as a for loop index, and then I'm just going to go do this. I don't care that the array hasn't been initialized. I want to go ahead and do this right here. Okay, and then just return. And the statement you probably do remember from Wednesday is that given our memory model, that this would prompt the program to run forever. Now, why is that the case? Based on this local variable set, we're dealing with this as an activation record. 1, 2, 3. This is the array. As far as that for loop is concerned, it's just one too small. This is the I variable. It goes through and it demotes all of these variables by 4. What values were there before? We have no idea, but it will certainly take whatever values happen to reside there and demote them by 4. Okay? Unfortunately, because the test is wrong, it goes up and it demotes this numerically by 4 as well. Now that 4 isn't so much a 4 as it isn't so much a -4 delta as it is a -1 instruction delta, because you know that this is the safe PC in our model. This was supposed to be pointing somewhere in the code segment to the line that called the foo function. This is planted down there in response to that assembly code statement. Does that sit well with everybody? Okay. When you do this, you inadvertently tell the safe PC that it wasn't pointing to this instruction, but that it should back up 4 bytes, which happens to be this nice round number as far as assembly code instructions are concerned, and to stop pointing there and to point there instead. So when this as a function returns, it jumps back to this right here, okay? And it executes the call, having no memory whatsoever that it called foo like 14 or 15 assembly code instructions ago, okay? Does that make sense to people? So this is this very well-disguised form of recursion. You won't be able to emulate this on the Solaris boxes or on the pods or the myths, because their memory model is a little bit more sophisticated than ours. They don't put the safe PC right next to this right here, okay? But nonetheless, that is this, like, probably the 5th example of infinite recursion we've seen in the last 2 days, okay? Let me show you another program. This is no infinite recursion in this one. I want to write a simple main program. Int main. I don't care about the parameters. I want to do this. I want to do, let's just say, declare and init array. Now, I'm not declaring any local variables whatsoever. Okay, and so you should already be a little bit suspicious as about what that type of function should do. But imagine a cs106a programmer in like week 4 learning C instead of Java, and they just don't have arrays and parameter passing down. So they have this right here, and then afterwards they have this thing called print array, and that is it. Okay, now unless there are global variables involved, there's no legitimate, even though we don't like globals, it still would be a legitimate way to communicate function information between function calls. But suppose there's no globals either. The programmer doesn't think they need globals because they do this: void declare and init array, and they just declare an array of length 100. They declare the for loop variable I. They're not going to overrun the bounds this time. They're going to get it right. And they're going to set array of I equal to I. Okay. So that's a beautiful little code snippet. It does very little outside the scope of the declare and init array function. But for whatever reason, they've decided that they want to declare this array, locally update it to be a counting array, and then leave. Okay? Then they come back and they want to print out that array, and this is not that uncommon when we taught in C. They think as long as they name the array the exact same thing, that all of a sudden there's a relationship set up between that array and this one, as if the word array has now been reserved throughout the entire program. And they do this, and then they do this for I is equal to 0. They get the for loop bounds right again. That's not the issue. Printf %d \n array of I. And they come in during office hours because there's some part of the program beyond print array that's not working properly. But then a TA looks at this, or I look at this and say, oh, well, this is wrong right here. And they're like, no, it's working fine. It's actually down here. Well, it may be something that's wrong down here as well, but clearly there's something wrong going on right here. However, they make the argument, well, it's working. And the answer is, it is working as far as they're concerned, because that manages to print out 0 through 99 inclusive. Okay? You all probably have some sense as to why that's happening. Try explaining that to someone who's never programmed before. Okay? This right here built an activation record of 104 bytes, goes down, and it lays down the counting array in the first 100 of, the top 100 of the 101 slots. Okay? Returns, it calls a function over there that has exactly the same image for its activation record. So it goes down and embraces the same 404 bytes. This is me embracing 404 bytes. Okay, and it happens to print over the footprint of this function right here. Okay, it's not like when this thing returned, it cleared out all of those bits and said, we got to scramble this so it doesn't look like a counting array. It doesn't take the time to do that. So basically what happens is if this is the top of the activation record and this is the bottom of the activation record, SP is descended once, this is filled up with happy information. Okay, comes back up after the first call returns, comes back to the same exact point, the happy face is still there. Okay, we print over it. Okay, and it happens to be revisiting the same exact memory with the same exact activation record, so it prints everything out exactly the same. Okay, make sense? Now there are some advanced uses of this where it really does help to do this. A lot of times, not in sequential code like we're used to, but about 11 years ago, I had to rely on this little feature when I was writing a driver for a sound card, and you had to actually execute little snippets of code with each interrupt with each hardware interrupt. And so a lot of times you had relatively little to do in one little heartbeat of an interrupt, and you had a lot to do the next one. In fact, you had so much to do that you weren't sure you were going to have time for it consistently. So a lot of times you would prepare stuff ahead of time and put it in exactly the right space so you knew where it was the next time without having to actually generate it. Do you understand what I mean when I say that? Okay, so if you write it, you almost think of this as this abusive, perverse way of dealing with a global variable. Okay, and you're setting up parameters for code that needs to run later on. Now, this example wouldn't exactly work that way. This isn't a great example of that, but at least it highlights the feature of this thing called channeling. That's exactly what this thing is when really advanced C and C++ programmers take advantage of this type of knowledge as to how memory is laid out. As far as the problem at hand is concerned, you feel helpless. You try to explain, for instance, if you've just put a call to printf right there, that its activation record has nothing to do with these activation records. So it goes down and garbles all of the sacred data from 0 to 99, and their response is, well, just don't do that. And comment it out, and they think they restored program, but they really have not. Okay, does this make sense to people? Now I want to revisit this printf thing, actually. I don't know how many of you know the prototype for printf. You really are just learning it. Basically, on the fly in context when you're dealing with assignment 4 and you're just seeing lots of printfs in the start code and you just kind of understand that there's a one-to-one mapping between placeholders and these %d things and %g things and the number of additional parameters. Well, sample calls are things like this, printf, hello. And that's in contrast to cout less than of hello, a string constant, with an ENDL at the end. When you have something like this, %d plus %d equals %d \n, and you want to fill it in with 4 and 4 and 8. If you wanted to do it that way, you certainly could, but the interesting thing from a programming language standpoint is that printf seems to be taking either one argument or 4 arguments, or really it takes anything between 1 and, in theory, an infinite number of arguments. It's supposed to be the case that those things line up in terms of placement and data type with the additional parameters. Okay? What kind of prototype exists in the language to accommodate that kind of thing? Well, we always need the control string. Okay? That's either the template or the verbatim string that has to be posted to the console. So the first argument to this thing, is either a char star or a const char star if the compiler supports const, and I call it control. But then there's no data type that's really has to be set in stone. There doesn't even have to be a second argument, much less a data type attached to it. I could put a string there if this is a %s, a float there if this is a %g, things like that. The prototype for that is ... It's like and so forth, whatever they want to type in. And the compiler is actually quite promiscuous, and what it will accept is arguments 2, 3, and 4, provided that dot is there. If you don't want to insert anything, it's fine. If you want to insert 55 things, it's great. The compiler is not obligated to do any kind of type checking between this and what this evaluates to. Okay? There's nothing implicit in the prototype right there. It's just I need a const char star, free-form char star, and then whatever you want to pass in. You want to pass in structs? Great. Pointers to structs, you can do that. GCC, for quite some time, has an extension to the C spec that it's implementing where it does try to do type checking between this and that right there. If you mismatch, it's doing a little bit more work at compile time than it's really obligated to do, wants to make sure that this printf call works out. Okay, so if you were to put %s and put 448 there, most compilers would just let you do it and run, and it would just lead to really bad things. Okay, but GCC will in fact flag it and say you didn't mean to do that. Okay, does that make sense? Okay. This return type, I mentioned this on Wednesday. This return type is the number of placeholders that are successfully bound to. So as long as everything goes well, it would be 0 for this call and 3 for that call. It's very unusual for printf to fail. Scanf, the read-in equivalent of printf, can fail more often. But if for whatever reason something goes badly, this would return -1. Do you know how IF streams set the fail bit to true so that when you call the .fail method inside C++, it'll like basically evaluate to true, and that's the way you break out of a file reading program? Well, you're relying on the equivalent of printf's return value, which is called scanf or fscanf, to return a -1 when it's at the end of the file. Okay. The reason I'm bringing this up is because based on what we know and the way we've adopted a memory model, I now can defend why we push parameters on the stack from right to left, why the 0th parameter is always at the bottom. The 1th parameter is always above that. Let's just consider that call right there. The prototype during compilation just says that either of these calls is legitimate, but when it actually compiles that second printf there, it really does go and count parameters and figures out exactly how many bytes to decrement the stack pointer by for that particular call. So the way that the stack would be set up, the stack frame would be set up is that this would be the safe PC that's set up by the call to printf. Above it would be a pointer to the string %d plus %d equals %d \n. This would have a 4, this would have a 4, and this would have an 8. Okay, that makes sense to people? The activation record for the first call would just have this many bytes and would have a pointer to the hello string. So the activation records above the portion above the safe PC actually is completely influenced, not surprisingly, by the number of parameters that are pushed onto it. Okay. Now, when we actually jump to printf, and this is where the SP is left, it doesn't have any clear information about what resides above the one car star that's guaranteed to be there. Does that make sense to people? So really all that happens, I'm going to draw this arc again like I did before, it knows about that much. Okay? There are special directives in the implementation of printf that allow it to manually crawl up the stack. Okay? But the number of arguments and the interpretation of the 4-byte figures that reside there, it can only figure that stuff out by really analyzing and crawling over this control string character by character. This is almost like the roadmap to what resides above it in the stack frame. Does that make sense to everyone? So the printf function really does need to get to the control string, and it reads it character by character, and every time it reads a %d, so let's say it reads the %d right at the front, it says, oh, the 4 bytes above the control string must be an integer. Okay, and then it sees another control, %d along the way. It says above that there must be some other integer. And this is how it discovers the stuff that should fill in the control string. Okay? You understand that otherwise, if it didn't have this right here, this would truly be a big series of question marks. It still kind of is a series of question marks. If this is the wrong roadmap, if I do %d plus %d equals %d and I pass in 3 strings, these things will be laid down as car stars. That's what the caller would do. Okay? And then it would interpret them as 4-byte integers. So whatever addresses happen to be stored there would be taken as unsigned integers, and it would just fill those 3 things in that way. Okay? Make sense? This is consistent with the way we push parameters onto the stack, from right, last argument first, then the second to last argument below that, etc., so that the 0th argument is at the bottom. Imagine the scenario where the safe PC is addressed by the stack pointer, but you have the mystery number of bytes below the control string. Okay, and that question mark region would be of height 0 for the printf hello call, and of height 12 for the printf 4 plus 4 is equal to 8 call. Okay, it would have no consistent, reliable way of actually going and finding the roadmap as to how to interpret the rest of the activation record. Okay, does that sit well with everybody? Okay, so as long as you understand that, then at least you have a defense for why that ... See, because of the ... the C-spec more or less had to, I guess they didn't have to, but it just made sense to, for compilers to implement this left to right parameter pushing strategy, okay, because they want to support that ... in the language. C++ has to do the same thing because it's backwards compatible with C. Java just recently introduced the ellipses, I think as of Java, I think it was either Java 1.5 or 1.6, I'm not sure, but very recently they introduced the ellipses. And so I just know, without actually reading anything about it, that they have to push their parameters on the stack in exactly the same way. Pascal, old school, wasn't old school for me when I was in college, but it's old school for everybody here. I didn't learn Pascal. I learned C first, but when I just read about Pascal, it doesn't have this ellipses option. You have to specify the number of arguments. It happens to press the arguments on in the opposite order. And it doesn't cause any problems. They had the flexibility to do it in either order because they never had to deal with this question mark region in a struct. Okay, does that make sense? Okay, but as far as structs are concerned, you may ask, this is a hard point to make. I'm going to try and do it. Struct foo. Let's say I have an int code, and I have, let's say this. Do this. Int code, and I'm just going to do that right there. It's unusual for you to have a struct around one data type, but I'm going to do it anyway. And then I have struct type 1, which has an int code, and let's say several other parameters. Okay. Maybe it's the case that the code inside a type 1 struct is always supposed to be 1. Okay, so just take this as a series of requirements of the example. If I have struct type 2 with an int code at the front, I might require that all instances of type 2 actually have a 2 at the front. The reason these are really esoteric examples. I'm just kind of making this up. I haven't done this in past quarters. But this right here is a data structure that I guarantee whenever I give you a pointer to a struct base, the idea is that there is one of two values that sits right there. Okay? It's almost like it's a little opcode in the assembly instruction in a sense, is to figure out how to interpret what resides or to figure out what resides above the 1 or 2 in memory. Okay? You could cast that pointer to a struct base knowing that there's going to be at least, or maybe it is typed to be a struct base, which means that you know that there's some kind of opcode or a type code sitting there. And then based on the result here, you could either cast this arrow to be a type 1 star or a type 2 star to figure out how the rest of the information is fleshed out. Does that make sense to people? A complicated example, but there are various structs that actually, I don't know whether you've looked at, I don't think I've exposed the code for all the networking and the URL connection stuff. If I did, you would have hated assignment 4 even more, because you would have thought you were responsible for it. But there are lots of structs that are afforded by GCC and G++ to help manage networking, and I tried to insulate you from that. Old school networking deals with 4-byte representations of IP addresses. They realized about 15, 20 years ago that they're going to run out of IP addresses pretty soon. So there's actually a 6-byte universal version of IP codes that it's standard, but it's not really widely adopted yet. There are 2 different structs associated for the 2 different protocols. The 4-byte version, IP version 4, there's IP version 6. The IP version 4 struct has been around for some 25, 30 years. Those things aren't going to go away. So when they designed the IP version 6 struct, they had to make sure that the first half of it had exactly the same structure as the IP4 version, and then they extended it with all this extra information. Does that make sense? So you always know that you're getting a pointer in networking code. You always know you're getting a pointer to one of those 2 structs, and you analyze the first few bytes to figure out whether or not you have an IP4 struct or an IP6 struct. Does that make sense? Okay. The reason I'm mentioning this is because now it kind of gives you some sense as to why the first parameter or the first field in a struct or a class actually has to be at the lowest address. It doesn't have to be, but that's just the way they did it because they had these types of things in mind. Okay? If this and this and this were always the last thing or a thing at the top of the struct in the activation record, it would always be at a mystery distance from the base address of the entire thing. Does that make sense? Okay. Now you could just argue that you just make int code the last thing in a struct so you can do it the other way. It just made sense for, to people who designed the spec or designed the compilers. I don't think it's part of the specification, although maybe it is, that the first field is always at an offset 0, and you can exploit that knowledge to do clever things with C and C++ structs. Okay. Does that make sense? Okay, very good. So I'm cranking on time. So what I will do now is I will give you a little bit of a heads up on how we're going to transition things. Everything so far in C and C++ has been sequential. And I'm talking in Java. It's actually not in Java necessarily, but all of the C++ and C you've done in all of 106B and 106X and first half of 107 has either been strictly or seemingly sequential. And you know what sequential means now because you're waiting for the sequence of RSS news feeds to all load over a 5-minute period while you test. Okay, so you know what sequence means more than you did a week ago. I want to introduce the idea of how two functions can seemingly run at the same time. That's going to be a huge win in the context of assignment 4. You'll all be delighted that you're going to revisit assignment 4 for assignment 6, and you're going to make it run oh so much faster by using this thing called threading. What I want to do is I want to talk about how two applications on a, and just give you very high level stuff, about two applications can seemingly run on the same processor simultaneously, and then use ideas from that to defend how two functions within a process can seemingly run simultaneously. Okay? Now I'll frame this way. Let's just think about one of the pods. Actually, let me draw over here. This is the virtual address space. Virtual means like the illusion of a full address space that make has while it's running. Okay, you don't think about make as an application, but it certainly is. It's designed to read in the data file that you call a make file to figure out how to invoke GCC and G++ and the linker and purify and all of those things to build an instrument and executable. This has a stack segment associated with it. All the local variables of the thing that implements make go there. There is the heap. There is a code segment. Okay. While make is running, it's probably the case that GCC as an executable is running several times. We'll just talk about a snapshot, a time slice where just one GCC is running. GCC is an executable. The first C compiler was probably written in C, or it wasn't written in C. It was written in assembly, but then it kept bootstrapping on the original compiler to build up more and more sophisticated compilers. So the C compiler was written in C, I'm sure of it. Okay. It also thinks its stack is there, and its heap is there, and its code segment, where all the assembly code stuff resides right there. I can tell you right now that they're not both all in the same place, okay? Because they do not share the stack, and they do not share the heap, and they do not share the code, okay? This virtual picture was in place so that make can just operate thinking it owns all of memory, and it lets the smoke and mirrors that the OS manages to map these to real addresses and map this to real addresses and map that to real addresses. It just wants to be insulated from that. Okay, maybe it's the case that you have I don't know, Firefox up and running on one of the Linux boxes, has the same picture, and then you have some other application like clock or whatever you have up there, and it has the same exact picture. Those are 4 virtual address spaces that all seem to be active at the same time. I'm going to call this process 1, I'm going to call this process 2, call this process 3, and I'll call this process 4. When I draw these little bands of segments right here, these segments is what they're called, they're all assuming that they have as much room to stretch out to make the stack as big as necessary, the heap as big as necessary to meet the demands of the program. But on a single processor machine, there is only one address space. This is the real deal right there. Okay, that's physical memory. And this has to somehow host all of the memory that's meaningful to GCC and make and clock and Firefox, or I should say the processes that are running according to the code that's stored in those executables. Does that sit well with everybody? Okay. Well, it turns out that this and that right there, they may have the same virtual address, but they can't really be the same physical address. The space has to be truly owned, or the values there in virtual space have to truly be owned by this process I've called number 1. Okay? So what the operating system will do is it will invoke what's called the memory management unit, okay, to basically build a table of, let's say that this is address 4000, okay? it'll actually build a table of process and something related to an address, and it'll actually map it to a real address somewhere in memory. Okay? Does that make sense? The idea, I think, probably makes sense to people. So that this right here, it thinks it's storing something in address 4000. If this is address, let's say it's address 60,000 is right there. Any request to manipulate or deal with address 4000 is somehow translated to a request to deal with the real address at address 600,000. Okay? Any type of load or store or access of this right here has to somehow be proxied or managed by this daemon process behind the scene, this thing that just runs in the background all the time, to actually map virtual addresses to physical addresses. And it knows that this address 4000 is the one that process 1 owns. So it just has this little map of information. I've drawn it as a map of pairs to physical addresses so that it knows exactly where to look on behalf of this process. It stores something to address 4000, it updates the 4 bytes that it reside at address 600,000. Okay? Now it doesn't really clip these things down at the 4 byte level. Normally what will happen is it'll allocate things, I don't mean allocate in the malloc sense, it'll just associate very large blocks in virtual address space, okay, with very equally large blocks in physical address space. So this might be some like 1K or 8K block of memory, okay? And if it's ever used, then it's sure to map the same size block or adopt some same size block in physical memory, so that address 4000 through like let's say address I don't know 4000 through address 8000 would map to whatever this is through whatever this is plus 4000. Okay, so there's some contiguous nature going on between all of the things in this virtual address space and what it maps to in physical space. Does that make sense? Okay. It's a lot of work. It's a very difficult thing to implement, certainly the first time. I've never implemented one of these things, so maybe it's even more difficult than I'm giving the impression it is. But it's doing all this stuff in the background. It's threads. It's all kinds of stuff that makes OS and systems code interesting but difficult. Okay. So we've solved the memory problem. In theory, you can run 40 applications. Usually it's the case that the stack segment is never really that big. It's initially slotted off to be fairly small for most applications, because unless you're going to like call Fibonacci of 1 billion, it's probably not going to have a call depth greater than like 50 or 60. In fact, when you have a stack call depth of 50 or 60, it usually means a lot of things are happening. Okay, the distance down from main to the subhelper to the 59th power function. Okay, I don't want to say it's unusual. Maybe 100 is normal. Maybe 200 is normal, 2 billion is not. And so you know that most activation records are on the order of, let's say that they're 1K, okay? It might be the case that you set aside 64K for the virtual stack, or the stack in virtual space. You have 2 to the 32nd different addresses, okay? 64K is like ridiculously small amount of that. It's like that. Okay, so it definitely has space for it. You could be more aggressive about the way you use the heap. You could allocate megs and megs of memory there. It's still going to be a relatively small portion of memory when you're talking about 2 to the 32nd different addresses. Okay, make sense? So the smoke and mirrors that's in place so that every single application can run at the same time and not have its address space or what it thinks its address space being clobbered by other processes, that's managed pretty well by the OS, not pretty well, ostensibly perfectly, okay, by this memory management unit. Okay, you can share address spaces across applications, but you have to use advanced Unix directives to do that. The part that is not clear, and this is going to become more clear hopefully next week and the Monday after it, is how the applications seemingly run at the same time when there's really only one register set, one processor digesting instructions at a time. I did this the first day of class, but it totally makes sense to do it again here. Forget about Firefox and clock. Let's just deal with make and GCC, which is what you've really been doing. And think about make and GCC actually running seemingly sequentially. You look at them both running, and my hands are sifting over their assembly code instructions. Okay, and they're both seemingly running at the same time. That's not what's happening. Okay, what really happens is that make makes a little bit of progress, and then GCC makes a little bit of progress, Make makes a little bit of progress, and this just all happens in this interleaf fashion so fast that you don't see any one lagging over the other one. Okay, it's like watching two movies at the same time where not much is happening. Okay, so you can actually follow both movies fairly well as long as it's clear that both of them are actually running. Okay, the argument for 2 hands scales perfectly well to 3 hands and 5 hands and 10 hands and 50 hands as long as the processor has the bandwidth to actually switch between all the processes fairly quickly. Okay, that makes sense to people, I'm assuming? Okay, now on a dual processor machine or a 4 processor machine or multiple core machines, it can actually really run 2 processes and 4 processes at the same time, but you can always run more processes than there are processors, okay, on any sophisticated system. If something's running a dishwasher, then it probably can't deal with threading. But if it's actually running some real program, it probably is dealing with a real processor, and the OS can actually dispatch and switch between processes fairly quickly, okay? Make sense? The reason I bring this up is because that, as a concept, is going to translate, I think, somewhat nicely to the notion of threading. This is multiprocessing, okay? Where several processes are seemingly running at the same time, and each process has its own heap and its own stack and its own code segment in its virtual space. Slightly different, but certainly related, is the idea that 2 functions in the same process, 1 code segment, 1 heap segment, technically 1 stack segment. We're curious as to whether or not it's possible for 2 functions to seemingly run at the same time inside a single process. Okay, you've seen this before. Trying to think. Like Microsoft, this is like Microsoft Office, like you're typing, and then while you're typing, all of a sudden in the background, there's some little paperclip comes up, says, I think you're trying to write a letter. Okay, and that happens in the background, and that's because something in the event handlers that actually catch your keystrokes have done enough synthesis of the string to look that it looks like a header of a letter, and so it spawns up this other function that it's not really supposed to interfere with your typing, and from a computational standpoint it doesn't. From an actual mood standpoint it does, because you actually go down and look at it. But that is an example of a thread that is spawned off in reaction to an event or something like that. Okay, that makes sense? iTunes, you buy an album of like 13 songs. I'm hip. I buy music online. And if you check the actual download screen, like 3 songs at a time are actually downloading. Okay, not really. It's really doing. Imagine there's another hand over here. Okay, and it's pulling things in little time slices. But it happens so fast, and the time slices are so small compared to what we can detect, that it looks like all 3 songs are being downloaded simultaneously. Okay, there's one process going on there. Okay, it's not like it spawns off a different executable called the paperclip executable. It's just some function to bring up that little widget. When you're downloading music, there's one process that's doing it. It is iTunes. And internally, it has some function related to the downloading of a single song that at any one moment, it's allowing to run seemingly 3 times. 3 at the same time. Does that make sense to people? So just imagine the scenario where there are 2 songs downloading at the same time. In that case, they both would be following the same assembly code block. They have the same recipe for downloading a song for the most part. In that case, the stack segment itself could be subdivided into smaller substacks where the stack frame for song 1 could be right there, and the stack frame for the downloading of song 2 is in this completely unrelated space. Not unrelated, it's in the same segment, but far enough away that you're not going to have one stack run over the top of another one. Do you understand what I mean when I say that? So when the process has the processor, it also subdivides its time to switch back and forth between the 2 threads. That's what you call these things, okay? And so basically it goes, you have time, you have time, you have time, you have time, hope you're downloading songs. Okay, and it just keeps doing that until one or both of them ends. Does that make sense to people? Okay. It shares the heap. Okay, so they all share the same call to malloc and the same call to free, and they all draw their memory from the same memory pool. there's only one copy of the code. You only need one copy of the code. It's read-only. It's fine for this stack and this stack to both be guided by the same set of assembly code instructions, as long as each one has some kind of thread identifier. Okay? Make sense? If the word thread is bothering you, just just take the phrase thread of discussion or discussion thread and just translate it to function thread. Okay? Does that make sense? Okay. You may ask what types of scenarios actually require threading and which ones really don't require threading. Let me just go over this very simple example as to how, a really simple example where you really would expect threading to be in place to model the real world situation. I will revisit this example on Monday. But I have this really simple program, int main, and there's no threading whatsoever. I have this for loop. Let's int num agents. When I call this num agents, I'm actually thinking about ticket agents who answer the telephone at like United or some other airline that still hasn't declared bankruptcy yet. Num agents is equal to 10, and let's just assume that the job of this program is to simulate the sale of 100 tickets for the only flight that happens to be flying anymore. Okay? You might do it this way. You might intrinsically hard code the 100 in there by calling some function, sell tickets, where you pass in I and you pass in 10. And I don't even have to tell you what sell tickets, I'll write code for sell tickets in a second, but the idea here is that we have to sell 100 tickets. This is the number of agents right here. That number is the same as there. In fact, let's say that there are 150 seats on the flight, so we don't have to mix tens. The idea of sell tickets is that it's supposed to be in place to simulate the requirement that some ticket agent actually sell 15 tickets before his or her job is done. Okay? As long as these run in sequence, okay, eventually you'll get to the point where you actually sell 150 tickets in this really rude but simple simulation. Okay? The problem here is that in the real world, it's just fine for all 10 of these agents to be answering telephones simultaneously. Okay? It's not, I don't want to start introducing thread functions yet, but I just want to leave you with the idea that we're going to be able to get that function right there to run in 10 different threads. In other words, I'm going to spawn off 10 different threads. All of them are going to be following the same exact recipe, where each one has to sell 15 tickets, and when a particular thread exits, we just know because of the way we code it up that 15 tickets have been sold. I'm not going to write code for this yet, but this is I think, a fairly good analogy. Imagine like a horse race or a dog race, okay? Sequentially, if you wanted all 10 dogs to get to the finish line, you could just let one go, and when he gets to the finish line, let the next one go, okay? And just do it that way and take 15 times as long or 10 times as long as you really need to. Or you can line them all up in 10 gates and lift the gates at once, and some will be faster than the other ones, but eventually they're all going to get across the finish line, okay? Like, you're basically pipelining and taking advantage of the fact that things can happen more or less at the same time. Now, the difference is that they don't run like this every time, and they're not respecting time slices. They actually are really independent agents, but we're going to try and simulate that idea as much as possible with this example when we introduce the thread library next time, okay? So I actually, this is a great place to stop because I'm kind of at the end of a segment in the course, and to try and introduce threading in 5 minutes would be, I think, pretty difficult. So I will see you on Monday. Today's Friday, right? Yes. Okay, and then we will talk more about threading then. I'll have a lot of handouts come Monday. Okay, have a good weekend.